In this problem, we're asked to find V0 of t for t greater than 0 using nodal analysis. We're going to use two problem-solving strategies. The first one's entitled S-domain circuits. Second one is nodal analysis. If we look at our problem-solving strategy for S-domain circuits, it says first, solve for the initial conditions in the circuit. If we look at our circuit, notice that both sources are multiplied by unit step functions, which says they have a value of 0 for t less than 0. So all our initial conditions are 0 in our circuit. So there are no initial conditions. The second step then says draw the S-domain circuit. So there's our S-domain circuit. Notice that we've converted the sources here. The current source is 3 over S amps. The voltage source is 10 over S. We converted all the elements to impedances. Step 3, we're going to apply nodal analysis. And if we look at our circuit, look at the number of nodes. We have a node here, 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 and here. So we have 4 nodes. We pick one as a reference. Let's pick this one as a reference, and that'll give us V0 because I'll define this as V1. This node voltage is V0. I'm going to call this node voltage V2. So we've got 3 node voltages, and we're going to need 3 equations. First, we have a voltage source, which means we get a constraint equation. So our constraint equation is V2 of S is equal to 10 over S. We need 2 more equations, and we'll get those equations by applying KCL here and here. So let's start with the node on the left. The current leaving through the 2S impedance is V1 of S over 2S. Then we'll have a current leaving through the 1 ohm. That's V1 of S minus V0 of S over 1. And that's equal to 3 over S, which is the current internet node. Now if we rearrange this equation, we can write it in the form, we have V1 of S times S plus 0.5 minus S times V0 of S is equal to 3 over S. I'm going to call this equation 1. Now let's go over and apply KCL at this second node, where we have the node voltage V0. And if we look at the different terms, we'll have 1 current leaving through that resistor. So we'll have V0 of S minus V1 of S over 1. And then we have this current, which is V0 of S over 2. And then we'll have this current, which is V0 of S minus V2 of S over 2 over S equal to 0. I'm going to call this equation 2, and I'm going to go back and call this equation 3. So our constraint equation is equation 3. Now, I'm going to substitute 3 into 2, and we do that and work and do some algebra. We come down with V1 of S times 0.5 S plus 1.5 times V0 of S is equal to 5. Now, I'm going to take this equation, I'm going to rewrite it. So, rewriting 1, we get V1 of S is S over S plus 0.5 times V0 plus 3 over S plus 0.5. Now, I'm going to take and substitute this in to this equation. Basically, I'll have one equation in terms of V0 of S. So making that substitution, we have minus s over s plus 0.5 times v0 minus 3 over s plus 0.5, and then we have plus 0.5 s plus 1.5 v0 is equal to 5. And if we rearrange again, so we have minus s over s plus 0.5 plus 0.5 s plus 1.5 times v0 is 5 plus 3 over s plus 0.5. Continuing on with the algebra, we can rearrange that expression to the following. v0 of s is 5 times s plus 1.1 over 0.5 s squared plus 0.75 s plus 0.75. Now let's factor a 0.5 out of the denominator. So now we have 10 times s plus 1.1 over s squared plus 1.5 s plus 1.5. So now that completes step 3. Now we've got a ratio of polynomials in s. So step 4, now we'll perform the inverse transform. First, let's factor the denominator polynomial and find the roots. So we want to know what are the roots of s squared plus 1.5s plus 1.5. Using the quadratic formula, we have minus 1.5 plus or minus the square root of 1.5 squared minus 4 times 1 times 1.5 divided by 2. So the roots then are minus 0.75 plus or minus j 0.97. So we've got a set of complex conjugate roots. So then we can write v0 is 10 times s plus 1.1 over s plus 0.75 minus j 0.97 s plus 0.75 plus j 0.97, and our partial fraction expansion will be k1 over s plus 0.75 minus j 0.97 plus k1 conjugate over s plus 0.75 plus j 0.97. And if we remember how we're going to solve for k1, we multiply through this expression by s plus 0.75 minus j 0.97. So we have 10 over s plus 1.1 over s plus 0.75 plus j 0.97. We evaluate that at s equal minus 0.75 plus j 0.97. And if we do that, we'll get 5.32, an angle of minus 19.84 degrees. Now, if we take that back to the time domain, we get 2 times the magnitude of k1 times the cosine, and here's the exponent of the exponential. So we have 2 times 5.32 e to the minus 0.75 t from there, and then we have cosine 0.97 t. Here's the omega, minus 19.84 degrees u of t volts. So then v0 of t is 10.64 e to the minus 0.75 t cosine 0.97 t minus 19.84 degrees u of t volts.